Okay, so in this little tutorial I'm going to do here, we've got our shaft. So this is my output shaft from my gearbox. And if we think about how this shaft works, we've got a gear sits on here, and the shaft spins on a bearing which will sit there, and a bearing that will sit there. Therefore, the axis of rotation is between this bearing and this bearing. Okay. And we need to control this segment of the shaft to prevent it oscillating as the shaft rotates on this axis. In addition, we need to load all of the shafts into the gearbox so that all one end are all flush with each other, and that end on this particular shaft is here, so that will be butted up against the bearing, and then everything else is spaced out along the shaft from that surface. So that's going to be another datum. So we've got two datums, this one here and this one here. Those two datums will be controlling the rotation, and this datum face here will be controlling the location along the shaft. Okay, so those are the key surfaces, key functional surfaces, and those are the key functional datums, therefore, because the datum system and the tolerancing system should replicate the functionality. That's really, really important. So you see how this is all triangulated. We can improve that if we want to, which will go up to options up here, to document properties, image quality. We'll just turn these up. Click OK. And there you go. It's nice and bendy now on those curves rather than flat. So this starts off by first of all making sure we've got Solidworks MBD live and that the component is all ready to go. I'm going to orientate the view to dimetric. So that's my back bearing, my front bearing, the output stub, and that's where the gear is going to go. This feature here, that's not really doing anything. That's just bulk material on the shaft. But it does provide this face that the bearing is going to sit against. So it doesn't matter whether you apply the dimensions first or the datums. Okay. In this case, I'm going to provide all the diameters where they are features of size. So that's this one, this one, this one, this one. This one is not a feature of size, so I'm not going to worry about putting the diameter on there or a fit on it. I'll just control that surface with a profile of surface later on. So I need my size dimension tool. I can click on this surface here, and I can specify the diameter. We're going to put a fit on there. It's going to be a shaft fit. But what size shaft fit do we want? Well, let's go and have a look. If I bring this up, we'll see normal and heavy loads, ball bearings, a bearing of between 10 and 17. You need a J5 fit. Okay, so this is information provided by the bearing manufacturers. Most bearing manufacturers they will have this information available, so you're not making this stuff up. You know, these are the tolerances that the bearing manufacturers recommend for their bearings. So let's go back to Solidworks. So we need a J5 fit. Here we go. And we need to set it to 3 significant figures. Oh, I've got it set for JS5 for some reason. Here we go. Let's change that to... Where's it gone? There it is. J5. And we need the envelope requirement on the end of there. So that's some controller form. You notice how this gets bigger and smaller, the text as you zoom in and out. Actually, it's just the object getting bigger and smaller, isn't it? We want this to scale with the object. And I think I covered how to do this in one of the other videos, but in case you've forgotten, details, and we're just going to set the scale to 1 to 2. Click apply. No, obviously I need to set it to 2 to 1. Oh, no, maybe not. Is that small enough? What do you think? Or should I try 1 to 4? Okay, that's a little bit excessive, isn't it? So let's go with 1 to 2. Okay, at least that'll lock it. So there's that first size. So let's go ahead and size up the other functional surfaces. So it's not this one, but this one. Now this is having the gear placed on it, so that needs a different size altogether. So again, we're going to go with fit with tolerance. I'm going to turn the parenthesis on. Let's go and have a look in this document here. We want an interference fit. So here's interference fit. Do you want a heavy press fit or a press fit? Well, we're going to be using keyways anyway to take the drive. So a press fit just to stop the thing from sliding up and down on the shaft will be fine. Here we go, this press fit here, we use a P6 with a H7. Okay, so let's go back to Solidworks. So we're going to set this to P6 for our fit. And then we're going to put our envelope requirement on the end. There we go. We've got our next bearing. So this again will have a J5. Now some of you might have noticed my deliberate mistake on this. I've been using J5, haven't I? Because I've been using it assuming that these bearings are all above 10 millimeters. So I need to actually use JS5. If we go back to our document, here we go, talking about tolerances. Below 10, we use a JS5. So let's go in here, set that to JS5. 3 significant figures. Don't forget the envelope requirement. There we go. And this one I'll have to just edit that to JS5. There we go. So there's our tolerances on for our bearings and for our gear shaft. This is the output stub. Now a length of silver steel shafting stock has normally got a H8 tolerance on it, so we'll use something similar. So we're going to use fit with tolerance, parenthesis, and we're going to set this to H8. There we go. So that's going to be undersized. And again, we just want to stick the envelope requirement on there. So that's our sizes all done. Now we can maybe drop on some datums. Datum A is going to be this bearing here. Okay, don't worry about how untidy it looks at the moment because we've still got to put on our geometric tolerances, and that will fix all of that. And we've also need this face here. So we click on there and pull that out. There we go. There's our datum C. So A, B and C are all set. Let's just reorient the view to diametric. There we go. We can now start to set our geometric tolerance. And now that we've got all the datum set and the sizes set, when we drop on our geometric tolerance, we can do all 4 of those one after the other, because we're all going to have the same type of tolerance on there. All going to have run out. 2 of them are going to have identical values. But we just need to set this to a compound datum, A-B. Now A-B is the axis between this and this. So it's the axis that the actual shaft is rotating about, is rotating between A and B, isn't it? So just trying to follow function. Now I've used 3 microns there, which is very, very small, because I'm supposed to use IT5 divided by 2 for my radial run out, which is only 3 microns. It's a tiny amount of run out you can have. If I'd used 12mm bearings, I could have had more run out, because my IT5 would have been for an over 10mm diameter, and that would give you a larger value, and we'll look at that later. So if I'd used 12s, I could have used a larger run out on this bearing. So there's that one. There's the other bearing. We next need to, this is set to only 2 significant figures, so I can't see what that value is. But we can do this one. This needs to be half of this, so this is 11. So at the moment we've got a 22mm band, so we need to set that to 11 microns. So we can have an 11 micron tolerance band. Let's just lock that on. There we go. So this one we need to set up with the correct value. So at the moment it's got 20 to 30 microns. Obviously we're missing the end figure. So let's go and have a quick look, see what P6 is. And then I'll reset that in a minute. So P6, 6 to 10. So this is odd, because this one here is over and including, and this one is up to and including. But that's the opposite way round to that other documentation. So P6 is 29 to 18, which is 11 microns. Let's have a look in here. Up to and including, 6 up to and including, yeah. Whereas the other was including and above. So this is more up to date. This is for the ISO documentation, ISO 286 I think it is. So if we go to an IT6, you've got 9 microns, 6 to 10, but we're on a 10 to 18 anyway. So there we go, we've got 18 microns. So we can use 9 for our, 10 to 18, IT6, we've got 11. Half of that's 5.5. You can't use 5.5 microns. So we're going to call it 6. And we'll drop that on. Okay. So I just want to change that to 3 significant figures. Hopefully I've got 11 microns there. That's it. So these datums, we want these to be attached to the tolerances, because they just look hideous like that. So let's move them. Here we go. So that's that one attached to that one. This one we need to attach to the geometric tolerance. There we go. So it just tidies it all up. It means that all the information about that surface is all in one place. It's the nominal size, the tolerance and the values of that tolerance, the fact that we're controlling it with the envelope requirement, and the run out and its own datum identifier, all of that is all in one place for that single feature. Okay, so that's quite useful. Let's look at setting up and controlling these faces here. So this face, this is essentially perpendicular to A-B. But with a turned object like this, sometimes we might use perpendicular, or we could equally use run out. They'll mean exactly the same in this particular case. So let's put some run out. So we're using total run out. And we need to set this to an IT5, which is 6 microns, because here's our IT5 thing. We've got between 3 and 3 is 6. There we go. So that's how we're controlling that. The other bearing butts up against this face. So here we need to use position, and we might only need like 0.1 or 0.05. I would say 0.1, tenth of a millimeter is fine. Okay, so position to what? A-B, and so A-B in there and C in here. So it's measured across from C, but the run out, it's measured across from C, but it needs to be in line with A-B. So first of all, it's perpendicular A-B and then located. But this is quite a wide tolerance band for that perpendicularity, so we're going to tighten that up. Again, we could use perpendicular, but because we're using run out at the other end, we'll use the same tolerance type. And in this case, we'll use the same value. There we go, 6 microns. Run out relative to what? It's going to be run out relative to A-B. There we go. So we're going to place that on the end of there. And we'll click OK. Now I think we need to just see this has gone grey. That's because we haven't referenced any datums for this. So let's edit this. Obviously we need A-B in the same way that if we were saying it was perpendicular, we'd need A-B. Okay, so that's now controlled. And we can move this to lock to it. Like that. There we go. So that's tidied that up.
Having a meeting now. Sorry, Michael.
So we've now controlled datum C, and we're measuring the other end where the other bearing is sat from datum C along A-B.
How's it going?
So the only bits we need to control now are that flat surface, that one, and that one. And we can just use position for this one, or profile of surface for all of them, to be honest, or position for all of them. And we'll use the same datum system as before. So although it only says AC here, you can see it says A-B C in there. So there's our profile surface. Then we can just go through and click on those surfaces.
Right. So, tell me.
Yeah, I tried to add more information on the methodology and objectives, but at the same point, I still have that library.
I'm just trying to see if I got your response from it. Right. Okay, I want to ask you a question.
Yeah.
But problem is, we may need some kind of commitment. Uh, I was approached by a company, and they want to make some validation of a design which exists.
There's
Basically,
our,
instead of being used, it's FEA. So it's a structure.
that's our basic view of all the surfaces that we've created so far controlled, and we can test to make sure they're all fully controlled. Aha, we've got one missing.
I can try to show what this is.
So geometric tolerance, and this is the surface that isn't doing anything essentially other than providing bulk support for that bearing face here. So profile of surface,
So
and again we can use
something very
A
different.
Okay.
But I'm not
dash
sure.
B.
How comfortable are you with FEA in Solidworks?
Yeah, right. I can still I can make myself better. 'Cause I do understand SolidWorks. Um, it's just in general. I haven't done much. What I would say, I did most of the everything that I did was based on. Uh, do you remember the plane?
Yes.
Yeah, that was basically most of the stuff that I did.
Yes. Okay. Yeah. So
There we go. And there's all the surfaces now fully constrained, hopefully. That's better.
what we have is this
And we
structure.
can maybe capture that view using this button here.
Okay.
And what this company wants to do is to make
There
sure
it is there.
structure is capable of
We're going to call it 3D view 1, that will do fine.
Okay.
being subjected to.
Okay. And it's as simple as that.